Welcome to this new episode of Video Wissen. Not too long ago we visited the ITER site and there is a video in the German channel Urknall, Weltall und das Leben about our visit of the ITER site, and I recommend you look at it. Even if you only look at the pictures, it was really impressive. And during that visit it actually came out that we also wanted to talk to the ITER director, Pietro Barabaschi, who happened to be in my office now. So today's video will be an interview with Pietro Barabaschi, director of ITER. We will speak a bit about ITER and mainly about why it is so big and how it was designed. So have fun. So as I said, it's a big honor for me in my bureau to host Pietro Barabaschi, the ITER director. Welcome, Pietro.
Thank you, Hartmut. My honor.
Yes, and as I said, we visited ITER some time ago, and there is actually a video about this on the German channel, Urknall, Weltall und das Leben, and you find the link below. And we were really impressed, and it seems like things are really moving at ITER now, right? You're sort of happy the way it goes.
Yeah, I'm happy. I'm certainly happier than I was 2 years ago when I joined the project. So 2023 has been a year of great transformation in ITER. We had also to do some repair work, as you probably saw when you
It's in the video
ITER.
as well, yeah.
And so we had to do this repair, and we had to restructure some of the assembly contract to keep a relatively faster pace. We also had to present a new baseline, and that happened at the middle of 2024. Mm-hmm. And we also had a council recently. The good news that I can tell you is that we come now to the end of 2024, and 2024 has been a record year for ITER in terms of execution. And also we have implemented 100% of what was planned. So this is really record twice in terms of percentage and total execution. So I'm quite happy, and we look forward to next year where we plan to implement even more work than the year past.
Okay, and speaking pro domo, we were of course very happy that you adopted a full tungsten wall, which is what we run in our local experiment R6 upgrade since years. So this is great collaboration.
Well, it is me thanking you that you have developed this important new technology. It's essential, and so I'm very happy that we took the courage to make this change and follow your lead.
Okay, so are we now. Okay, that's one thing, and this is actually what I mainly wanted to talk about today. As people will see in the video, ITER is really big. I mean, everything is big. You see, I don't know how often during the video I said, this is really impressive because you look up like this. And so, of course, people ask themselves, why is it so big? And I think you're the best person to ask, why is it? Why is ITER the way it is?
Yeah, it's a very good question, Hartmut. And it's a question that actually, surprisingly, I don't get so often. Mm-hmm. So I'm glad that you're asking me this question, and I get the opportunity to try my best to give an explanation in very simple terms, let's say. Okay. So ITER is not the size it is because of some megalomania, some mania of grandeur, let's say. It is because of its objectives. So the essential objective of ITER is to sustain for a long period of time, say in stationary conditions, so to say, fusion condition where the self-heating will be dominant. So it will be much bigger than the heating which is injected from external means. So as I gather, I presume you have explained in other, of your videos, we need to attain a certain triple product, the Zohn criterion. You have explained that, right?
Yeah, so several times it's the NT-tau thing, but actually I think it's maybe not such a bad idea to write it.
Maybe I should write it here.
Yep.
So what we have to do is that we have to attain NT-tau E greater than about 30, 10 to the 20. And the units here are kilo electron volt. They are seconds for the energy confinement time, and cubic meter or 1 over cubic meter for the density. So as you probably also explained, the temperature itself is something which is about 10 kiloelectron volt.
Yeah, this
in
is
the order of that.
Because of the cross-section being such that if you average over the Maxwell distribution, it just favors this, and this is the best access condition, right?
Thank you for explaining much better than I could. So you can really play with these two parameters, density and energy confinement time. So let's start with the density. The density is not really a free parameter, as you know well in a tokamak. We need a magnetic field to confine it, to make sure that we confine the pressure that comes as a consequence of the product between density and temperature, because density and temperature represent a pressure, which is about 8-10 bar in the center of ITER for the magnetic field that we have. Okay, but so it is related to the magnetic field. The magnetic field pressure, we call it magnetic pressure. The magnetic pressure, which is necessary to contrast the kinetic pressure, is, let's say, proportional to B to the square divided by 2 mu naught. So let's say this is a constant and this is the magnetic field. So we have essentially, because the temperature is constant, that the density is essentially proportional to the square of the field. So when we increase the field, we can increase the density. And it is mainly due to stability reasons. Incidentally, the ratio between the kinetic pressure and the magnetic pressure is what you physicists normally call beta.
Yes, and which is unfortunately pretty low, because you would like the magnetic field pressure to completely balance the kinetic pressure, but actually this quantity beta, the ratio of the two, is only of the order of a few percent. We talked in a different video about this. This is just the way it is.
Okay.
And I don't want to play the professor too much, but for everyone who has listened to the video so far, it's just very interesting to point out what Pietro said. N and tau E are the parameters, and we end up with seconds and 10 to the 20. And if you've seen the videos on inertial fusion, there is 10 orders of magnitude difference. So I have 10 to the 31 and 10 to the minus 10. So it's really different, but the product is the same. So this is really universal, right?
Exactly.
Okay,
exactly. Very good. Very good. Very good.
Yes.
Say parenthesis here. So okay. So we have basically this relationship, which is a very important one. So now, when we have in ITER, we operate with a field which is about 5 Tesla in the center, about 12 in the conductor. We end up with a density in ITER, which is an ITER, let's call it, which is about 10 to the 20 particles per cubic meter. So when we then consider that we have to achieve this triple product with 10 kV, we have a necessary energy confinement time, which is about 3 seconds. So that is for ITER. Now, energy confinement time, we don't have other than a scaling law that we could study during the last decades. You are, of course, a big author of the work that led to many of these results. And when we look at the history, say, of studies in terms of confinement, we essentially come down to a relatively approximate but simple formula that tell you that the energy confinement time at the end for a tokamak with an aspect ratio of about 3, like ITER, it's the volume, which goes with the cube of the radius, multiplied by the square of the field. So when we again plug in the numbers that we have and the energy confinement that we require, I mean, this is a proportional, it's not an equal.
Yeah.
There is a coefficient here.
Yes.
When we plug this in, we end up with a radius which is about 6 meters. So this is how we end up on the needs for the ITER design with this specific magnetic field.
Yep. So this is more or less, I mean, you can almost do back of the envelope if you know the scaling, how to dimension it, and there is no way around. I mean, this is clear that you cannot do this with the magnetic field pressure we are given, and so this is where you end up. And I think an interesting thing which we talk about in the video sometimes is that there is at least the idea to use much higher magnetic field, which technically is very difficult in terms of forces and stuff. We talked about this. So in principle, you could argue that if you increase the field, you can make the thing much more compact and you can decrease the radius. And so first of all, I think the technology was not there when ITER was designed, but I think even now there are problems with it. So maybe you could...
Yeah, so of course the question is, if the energy confinement time is r cubed b square, and therefore n t tau e will be proportional to r cube times b to the fourth power, because you will see that
the density goes exactly in here. Yep.
Then, of course, the obvious question is, okay, why do you need to make it 6 meters? Increase the field, then you can quickly reduce its size. And that's a very fair question, and it's not a new question.
Yes.
It's, of course, as simple as it is. It is a question and a debate that was taking place also in the 80s, in the 90s, about going towards high field and high density. Now, here I have to explain another thing, is that when we come to the fusion power that is generated, this, of course, depends on the volume and depends on the power density. And the power density goes with the square of the product of the pressure, essentially.
Yeah.
So the fusion power is also proportional to the volume, which is r to the cube, times b to the fourth power, which is quite interesting, because...
Just to say this comes from the fact that you might have been too quick.
Yes.
So n times t is fixed. N we have b squared. N times t is the kinetic pressure. So if you have the kinetic pressure squared, it's actually beta squared, the ratio squared, times this b to the fourth. So this is where the b to the fourth comes in now.
Okay, sorry, I was too quick.
No, that's fine.
That's okay. But you see that you increase n t tau, you want a certain n t tau, you're going to get a certain fusion power, whether you like it or not.
Yeah.
Okay, so now I want to open a parenthesis, which I think it's interesting when we look at fusion as an energy source. Fusion has something specific, which is somewhat different, for example, from fission or from a fire or other type of volumetric sources. Fusion is very unique in the sense that you cannot really embed the coolant inside the medium that generates the power, because the medium needs to operate at 150 million degrees. So there's no way to put, say, cooling pipes and whatnot. You really have to absorb the power at the edge, on the surface. So now it turns out that in ITER we have about 500 megawatt of fusion power, which are generated. And by means of the way the tokamak works, some of this power is relatively concentrated. It's not spread uniformly. It is spread to some extent with some uniformity, but there are some, say, regions which are particularly loaded.
Parenthesis. I think people remember. I think I've drawn this 1,000 times in the videos. This is what we call a diverter. Torus is like this, right? The heat comes out here, but then it goes in a very narrow region down here into the diverter region, which is only of the order of centimeters. We have stuff about, remember, the X-point radiator, the compact radiative diverter, the stuff with the edge-localized modes. We were always talking about overloading, really, this diverter structure, which is the one which gets all the heat. So what you speak about, the small area, is exactly what you're referring to here.
Exactly. Yeah. And I'm glad you made your video about this, because it's one of the big challenges in fusion. And this has been actually a driving parameter for ITER itself, because with the 500 megawatt of fusion power that we have overall in the machine, we have something in the region of 15 to 20 megawatt per square meter of incident power flux in the diverter region, and some megawatt per square meter on the first wall. So now this is really at the boundary of technology. Just to give you an example, on the surface of the sun we have about 50 megawatt per square meter.
So we are not too far.
I mean, one may say, okay, and we need to cool it, not for a few seconds. We don't want just some material to withstand a few seconds. I said it at the beginning, it needs to be stationary.
Yes.
So it needs to be cooled by something which looks like a radiator.
Yeah.
Now, radiator here, just to give an example, is about 1 kilowatt per square meter. So imagine a radiator that needs to emit or absorb 10,000 or
Yes.
15,000 times more. So to do that, we use some special type of cooling channels which are coated or embedded in some matrix of, we used to use graphite and now we use tungsten, which can resist very high temperature. So now you can imagine, would we increase the field in ITER, for example, something that, by the way, we could have done, we could have decided to do even 20 years ago. It's not that we had to limit ourselves to 12 or 13 Tesla in the conductor. We could have gone to higher magnetic field in the conductor. Then we would have increased this power density even further. And that increase was deemed to be, say, not acceptable. So this is fundamentally why ITER needs to be big. It maybe could be a little bit smaller, but maybe could also be a little bit bigger, and because the power density cost, when you have to deal with extreme density of loading conditions, this bears a cost. It's not just size, you know. So in terms of cost optimization, it was decided to strike this balance at about 6 meters.
I'm glad you mentioned that there were previous studies which looked at much higher field. Of course, the studies in the 80s were mainly based on copper coils, so that was anyway something which would consume a lot of electrical power because the copper coils just heat up by the Joule heating. But also they were not looking at steady state. You said you want to be stationary on the plasma timescale, also on the timescale of the components. So in principle now, if you have high temperature superconductors, you could go this way. So you said one of the obstacles, of course, as you reduce at the same fusion power, which is given by the collinearity of these two scalings, you reduce the size, you will have a larger flux, and it will actually go with a square because of the surface. But there's also technical challenges, right?
Yeah, there are technical. So if I may say first, I would like just not to be misunderstood. I think that it's positive that there are always research activities to try to push the limits. And doing so in some specific dedicated devices which can try to increase the field, maybe using some new technologies such as high temperature superconductors, and then in turn leading to extreme power densities and having to develop the technologies to deal with that. That's all good news, you know. So I think this will then provide a number of technologies that can only benefit the future development. But ITER had, of course, to develop a plan that had to be relatively, let's say, reliable upon the scrutiny of the many stakeholders that we had. Now, you mentioned also something else, which is, of course, that played also a role in the optimization of ITER. This is also quite interesting. If, for example, we would, let's say, magically be able to deal with any power density, and we would, yes, be able to reduce the size. But some things don't quite scale linearly. So when we reduce the size and we increase the field, we have, it's not just like a photocopy, you know, you cannot just make things smaller, because what really happens is that the magnetic field that goes up rapidly needs in turn to be contained, let's say, and to do that you need structures, and these structures are made of metal. And even at cryogenic temperature, the metal you have seen, the coils, and they are mostly stainless steel, actually, the coils that you have seen. Most of its weight is stainless steel. It is extremely loaded mechanically. And so you need to deal with the very, very extreme loading conditions. So the magnet, relatively speaking, becomes fatter. As you Xerox down, if you photocopy down ITER and you increase the field to attain the same anti-tau, you will see that the plasma gets a little bit smaller and the magnet gets a little bit bigger. And at the same time, the shielding itself, which is protecting the magnet from the neutron flux generated in the plasma, cannot be halved, for example, when you halve the size. Because the attenuation in the material, the attenuation of neutrons, is non-linear with the thickness.
It has nothing to do with the magnetic field. It is just the 1/E length of how the neutrons are eaten away by the shielding.
Exactly. So almost that thickness remains constant. So as you reduce and you want to operate in steady state, even having a magic material can withstand any power flux, it would still have this problem that you have that the shielding itself become relatively speaking very large, and then the power becomes smaller, and you need to increase even further the field to achieve a certain empty tau.
And the stuff with the forces, just to say this is actually a pretty universal formula, because this is the magnetic pressure. We only talked about the magnetic pressure in the plasma. Of course, this is the magnetic pressure or the force that you have in the coil as well. So it actually goes with a B squared, which is very important. So if you double the field, the forces, or say the stresses, will go up by a factor of 4, which is pretty strong.
Exactly,
yeah.
Exactly. Very well put. So the essential really it comes down that the essence of ITER having to be this big, it's absolutely correlated with the fact that it needs to operate in stationary conditions. Would we have had the objective to attain the triple product, say 30, 10 to the 20, for let's say 5 seconds, it would have been a completely different optimization. Yes. It would have been possible to reduce it. It would have been possible to reduce the shielding because we would have not been concerned about the temperature increase. And then we would have a short 5 seconds, wait an hour, and then have another one, which is pretty good when you want to do a physics experiment. Yeah. But when you want to go into the getting closer to what will be the need of a power reactor, which should not work by bursts, but should work with continuity, because at the end, it's the energy you produce, not so much the power. Yeah. It's the energy in total that you produce that counts. There you go. Then you need this big size.
I think actually I explained this in the video to some degree. It's actually the difference in cooling between ASTIX upgrade and W7X. ASTIX upgrade does run for 10 seconds and all the temperatures in the components climb linearly, and then you turn it off and it cools down. And since W7X is supposed to run for minutes, actually did 8 minutes some year or 2 years ago, everything goes to steady state. So you have to cool it like it goes. It increases, but then it levels off and it sits at a certain temperature, which is much harder from all points of view. So I think this really puts it into perspective. And I think that the way you said it, this is also, I think ITER as a project from taxpayers' money was clear that it should be designed such that it works. So you went this way. I also think it's a great thing that people research in all directions, try and push the limits, and maybe the second generation of fusion reactors is like this and like this. So we should never stop this. But I think for ITER this is a very good.
I think it's a very good idea. And if I may, I want to take an opportunity to say that from my perspective, all what we see, that there are so many private sector initiatives to develop and push boundaries, I think it's a very good idea.
Yes.
And we have established, take the opportunity to say that we have established now a framework where we will work with many of the private sectors initiatives that are around the world, where we want to give them our support, because we have a lot of know-how coming to some extent from people like you also that gave us the know-how, but we have developed a lot of know-how on what to do and sometimes also what not to do, which is also very important. Very important, not always published, as you know. And so we have started this with quite a lot of success. So we work together with the private sector, so in many fronts.
Okay, thanks a lot, Pietro.
Thank you, Hartmut.
Pleasure to have you here.
My pleasure.
And as always, if you like the video, or even if you have points that you would like us to expand further on, you can leave your comments down here and we will read and try to accommodate.